today's speaker is Oleg Musin, and he's going to speak about sphere pockets in 4 dimensions. So, Oleg, please.
Thank you for this invitation. I would like to share with you some result and ideas about sphere packing in 4 dimensions. I have 1 hour 20 minutes, right? Correct? Is that correct?
No. You have about 1 hour actually.
Okay.
So, 1 hour and 20 minutes usually, but if you.
No, I will try to be within 1 hour. Okay, thanks. Thank you.
Okay, good.
Let us start from the history, from this old story. The first known result about sphere packing in dimension 3, about sphere packing problem. It happened. You can count how many years ago in 16th century, when Sir Walter Raleigh, it is a famous person in British history, organized the first expedition to North America, and his assistant was Thomas Harriot, who just recently graduated Cambridge, probably, I don't remember, one of university, and he asked him very simple question: how to find how many cannonballs can be we can order from cannonballs that can be packed in the given volume, in the given container. Yeah, Harriot discovered a formula, like they knew everything coming about volume because it is, and he discovered that it's about, if we have a container, sufficiently large container, that it's a number of cannonballs can be, it's about 74% of, I mean, density is about 74% of this volume, namely it is the pi over square root of 18. You can see this formula. He continued here. We can see one of packing, one is optimal packing, but because there are infinitely many, actually, it is strange. But in dimension 3, if you there are infinitely many. Moreover, it is continuum different packings of the same density. It is completely very different from dimension 2 and 4, and probably 8 and 24. He continue think about, I mean, Harriot continues to think about this problem, and it is known that he also considered packing circles into a square, another several other problem, and he sent, what is known, he sent a letter to Johannes Kepler, who was mathematician #1 at that time. He sent him letters, 2 letters, as I remember from history, explain what his result. But what is published, okay, and George Spiro, who wrote a book about Kepler conjecture. I like this book a lot. It's my historical about the history. It is I took from his book. And George Spiro said, you know, it is we have to call this conjecture not Kepler conjecture, but Harriot conjecture, or Kepler Harriot conjecture, something like that, because actually he sent to Kepler letters about sphere packings, about its formula, what he found. But Kepler in 1611 published beautiful, actually, book, some little booklet. I see this book. There is some translation into English translation, where he gives some gives us this formula, and he actually he knew that there are infinitely many packing of the same density. He knew many things about sphere packing in 3 dimensions. But you know, one of the important things, he actually not mentioned name of Harriot. That means, you know, actually it is, and after him, you know, this mathematician thought that this discovered by everything discovered by Kepler. It is some relations between British and I don't know this, because you know they try to explain that it is actually it was discovered 20 almost 25 years before Kepler. However, I think actually it is not maybe it is well known because even before, because it is not too complicated to find this formula. Actually, it is possible just even maybe 2,000 years ago. People knew this. It's about this density packing. What happened later? It is a published book, beautiful book. By the way, it is called The Six-Cornered Snowflake. He explained many things. You can see here several questions, but the Kepler considered several questions, but actually about why snowflakes is six-cornered. I mean, argument is not actually it was not complete. I know that only in the middle of 20th century, some Japanese scientists got Nobel Prize for this explanation. By the way, the form of snowflake is not so simple, and the snowflake usually six-cornered when we have a very low temperature, like minus 15, 18, something like that. That means, you know, that time in Europe it was very cold weather. I mean, not like now. Okay, and this become Kepler conjecture. This we have a Kepler conjecture about previous, like this density in three-dimensional spaces, pi over square root of 18. And after many years, it has become of part of Hilbert problem, because it was not solved up to 20th century, and it is a problem 18.3. The third part of this, the Hilbert problem 18, and actually what Hilbert did, he considered more general question, namely about equal solids, packing of equal solids. It means not necessarily to be, and they especially mentioned this case, namely the most densely packing of the sphere of this given radii. And only in this case, among all problems, Hilbert also mentions that it is an important question in physics and chemistry. No, it is clear because we have some molecular structure, and Hilbert. It's only one application. All other problems, you know, not related to application. Okay. Next story happened 100 years later. Namely, it is another packing and sphere packing problem. It is a Kissing number problem, and let me briefly explain this problem. David Gregory, actually, he's one of the first who followed to Isaac Newton. He was an astronomer from Oxford, and he visited, even on that day, he visited Newton May 4th, like almost you can count. It also it was a May, but not May 7th, May 1st, 1694, and they considered many. They discussed many different questions, and one of them was about. It is about Kissing number, what we call Kissing number, namely how many non-overlapping sphere of unit spheres can touch the center sphere. Yeah, I will show you later some pictures. and the discussion actually there is example of its 12, but let me show. Like here, like we have 12. It is located in the vertex of icosahedron. You can see. Take a look at this. But we have we can see that there is some gap between spheres, and yes, there is a feeling that if you move all of them in one side, that enough space for certain sphere, right? And moreover, it is known, there is actually a notebook written by hand of Gregory, as well as Newton also added some lines there. Yeah, there is arguments by Gregory who actually give some arguments if he divided by area of spherical caps, because spherical caps of radius pi over 3, and he divided area for pi, area of a sphere divided by this number, and he obtained 14.9. That means, it's almost 15. It is almost 15 times area of a sphere greater than area of spherical cap of radius 30 degrees. But however, okay, that's probably Gregory arguments was okay. 14 is possible, not possible, but 13 probably possible. And the one question, usually people ask question, why they cannot some experiment, but it was impossible that time because only cannonballs, billiard was discovered in this game. I mean, billiard game only in 18th century. It is. Can you imagine the two professors, right? Two professors go to try to do some experiment with cannonballs. It was impossible. They tried to solve the problem mathematically. Okay. What is first publication? There are some experiments also. If you can look at the George Spear book. By the way, what is it? George Spear. He is not mathematician. He got master's degree in mathematics, but now he is political journalist. Yeah, and he wrote a book. Wrote a book about sphere packings by a political journalist. It's very interesting story. You can okay. Anyway, the first publication. There are some experiments in 18th century, but first proof about first mathematical proof it happened in 1831 by Carl Friedrich Gauss. He proves the following fact. We know this face-centered cubic packing that like this one, like this one, right? It is called FCC, face-centered cubic packing. If you think about that, it's a lattice packing. That means centers of the spheres, all of they placed on the lattice. There's a node. There's all of them, are nodes of lattice. It's called lattice packing. We can any lattice. We can consider any lattice, and we can, if we said that this packing is a lattice packing if centers are nodes of lattice. Okay, and Gauss proved that in 3 dimensions, the FCC packing is the unique densest lattice sphere packing for dimension 3. Yeah, it is actually it is a beautiful proof. I gave several talks about his proof. It is only 40 lines. It is his actually it was his Gauss review for the Seberg, I forgot name. He wrote a book about ternary quadratic forms, and he has a hypothesis that conjecture. He had a conjecture that is equivalent to this result, but he couldn't prove it, and he proved some weaker inequality. And in this book, it was 300 pages, and 200 pages he considered in 200 pages he considered different examples, but Gauss spent only 40 lines to prove that. It is beautiful, absolutely understandable. If you look at that, it is like you realize that this guy is genius, because it is something extremely interesting. Because it is understandable for high school students, because it is only some try to prove inequality. He represent he can two cases and represent the sum as the sum of squares. It means automatically gives greater or equal to 0. Okay, and many mathematicians try to understand his Gauss proof, and they thought that maybe there is some hidden principle. You can see here some names in Mead, Beck, Selling, Minkowski, Mother. And the last publication, by the way, is not like less than 30 years ago. Succeeded two Russian mathematicians, actually the state students of Chebyshev. They published 3 papers in 1872. They considered they proved they solved the lattice sphere packing in dimension 4. Namely, they proved that D4. The answer is D4. Lattice is D4. And in dimension 5, the lattice is D5, and conjecture it. They found example. It was a paper between probably these cases. So I don't remember, or maybe less, something like between 1872 and 1878, maybe. Yeah. And they conjecture, they made a conjecture about dimension 6, 7, and 8. And this dimension 6, 7, and 8 was solved only many years ago, like 50 years ago, in 1925, 29, 1935. Bliefeld proved conjecture, Korthenkulter of conjecture for dimension 6, 7, and 8. Yeah, and next happened, it was published 2009, but conjecture, first announcement, first presentation was 2003, because I've been together in the same meeting in Berkeley. It is Conne Kumar proved that Rich lattice is also the densest lattice patent in dimension 4. Okay, and by the way, if you look in this table, I remember my discussion with Levenstein and Vladimir Levenstein. He is a famous mathematician. He's very famous in this area. He told me, something happened something happened in this area. I mean, the sphere packing, Kissick number, something. I mean, serious once in 25 years. But I remember this discussion. It was like 2003, 2004. I said, okay, no, very soon, probably will be solved some problems, and maybe sphere packing also in 4 dimensions. But he was not right, because the next it happened 2016, say 2003, right? 2016, 13 years later, when Marina Vizovskaya proved about density packet in dimension 8 and 24. So maybe now it is, I don't know, maybe we need now maybe to find, maybe it happened maybe 5 years, 10 years, maybe. But it is true. It is, if you count the number of years, it's something like the average. Okay, let us consider a general case, namely, let us consider a case not necessarily to be lattice packing, any packing. The first announcement appeared first about that the hexagonal lattice is the densest of all possible circle packing. Both, I mean, it was claimed by Axel Thuer, a famous Norwegian mathematician, in 1890. But most of experts doubt that he had a proof. It is known there's some discussion here actually with Minkowski that Thuer said that I have a proof, but it was not published, and only a conference presentation, and some abstracts was in Norwegian. Some like it is clear that not many people can read it. I mean Norwegian, and after several years later, also he wrote something. Okay, anyway, it is definitely the first. I believe the first rigorous proof is published by Laszlo Feistot. It's the great discrete geometers. Actually, he's a founder of discrete geometry, and he proved it in 1940. 1940, he considered. Actually, in his book we can see actually 5 proofs. Yeah, 5 different proofs. If you look at his book, unfortunately, but it was only I know about it. He wrote this book. His book is in German, 1953, published in 1953, and translated into Russian, 1958. Yeah, it is a beautiful book. But recently it was translated by Gabor Feistot, his son of Laszlo Feistot, and Wladimir Kuperberg. In English, it will be published soon. It is amazing. Can you imagine the first publication 1953 and 2020 will be translated into English. Okay. What is interesting that I thought everything known in planar packing, right? But with Anton Nikitenko. He's now in Austria, postdoc in the Institute of AIST, Institute of Information Science and Technology, and at that time he was a student, and we considered periodic packings. Or just in other words, it is we have a square torus, flat torus, and we consider the following problem. Let's we have n circles and points, or n circles that matter, right? And circles to package that in the package that in torus or periodic packing with given number of n with a maximum radius. Okay, there are some. It's not complicated to solve this problem up to 5 probably, right? But the problem is first problem it is in 6, and we consider 6. And what we obtain that for n equals 7, there are 3 optimal, just not 1, just 3. It is not never happened in a spherical case in Tammes problem, but it happened. It happened in okay. It is one of them, and moreover, it is we have isolated circle also. We can see this example, right? One of them is isolated, and we have 2 another packings. This one it is like normal packing, but of course there is some gap. But however, it is a maximum. I mean the optimal packing, and the third one. It's not saturated because here enough room to place one more circle. I mean, you can do that is solution for n equals 8. So even for this simple case, because it looks like very simple, but however, it is the problem is solved only up to n equals 9. Oh, sorry, n equals 8. We have a conjecture about 9 points, but I recently, several months ago, I received some numerical solution, but I don't know what happened with this case because it is not there is some gaps there, but I don't know. It is still probably still is open. Yeah. As well, so of course, there are even for spherical periodic packing, because there are many cases, not necessarily to take to consider square. You can consider like any rhombus or I don't know, parallelogram. This because you pay periodic. And actually, there's a lot of things to do in this, even for torus. Also, you can understand, explain everything for high school students. I mean, for the problem. But still, after I don't know how many 400 years, still there are open problems. Okay, let us return to Kissing number. First, actually, there are many proofs. Such, I mean, many, even some of them were published. For instance, Hoppe published solution of the certain sphere problem that that Kissing number in dimension 3 is 12. But there is some gaps. Actually, Thomas Hales published, you can see the reference here in Mathematical Intelligence, 1994, a counterexample for Hoppe proofs. But there are other attempt. But finally, this problem was solved by Kurt Schutte and van der Waarden, sorry, in 1953, and they finally prove that the Kissing number in dimension 3 is 12. And but it's not as a story, that is a story, because John Leach, this famous John Leach, published two pages sketch, beautiful. I remember this has this proof, beautiful proof, actually very interesting. The problem is it is not complete. And this is a story from Günther Ziegler. It is written, by the way, if you look at the second edition of the book of Agner and Ziegler, proof from the book, they wrote in the second edition. It also missed one of the old chapters about the problem of the shooting spheres, which turned out to need details that we could not complete in a way that would make it brief and elegant. Actually, what happened, what he told me, is that they received several angry letters from readers that they could not, it is very good written, everything great, some pictures, but however, there is some gap. And they agreed, I mean, like also agreed on this book, and actually they removed this chapter from the book. It is, it's about 2000, say 20 years ago, it's about 2000, people realized that one of the oldest problem, the Kissing number, about Kissing number in dimension 3, it still has no good, has more some proof that we can explain to students. And you can see here several publications. What happened after that? Maybe I just at my list, it is not like, maybe not recent. Yeah, and Hiroshi Meiharo, actually, my favorite is Hiroshi Meiharo proof. But Igor Park told me that he used my proof, 2006. They're different because Hiroshi Meiharo continues this, to use some geometric proof, but my proof and based on relies on Del-Sutton method. I mean, some idea what I would like to briefly discuss also today. Yeah, still probably we need someone who will just to find some good solution for this for solution for the certain sphere problem. This is Gregory Newton problem. Okay, Kissing number. Like, okay, we know for Kissing number the status for Kissing number what we have now we have now, we know, of course, it's a Kissing number. It is in the dimension 1, it's obvious, as well as also very simple exercise that Kissing number in dimension 2 is 6. I mean, we have a, if we have coins, coins on same signs, right? That of course it's easy to see that only maximum 6 can be. It is just for kids, exercise for kids. I mean, for those 9th grade students maybe. And for dimension 3, I told the story. I told the story about dimension 3. It is Schutter-Waterwagen. And it is like a regular story. Yes. And in the dimension 4, I proved that the Kissing number 24. However, big open problem already. I don't know how many years, like I don't know, 50, 60, 70, I don't know exactly, that this Kissing arrangement is unique. We'll discuss a little bit later some details about that. So, and 2 dimensions, special dimensions, 8 and 24, it was independently proved that Kissing number dimension 8 to 40, and Kissing number of dimensions 24 is 196,560. 560. It is proved by independently by Adlisco Sloan and Vladimir Levinstein. Yeah, 1979. Okay, and nothing more. Yeah, people, there are some bounds, but no more solutions. Okay, and one more problem. I just let me briefly discuss. One of extensions of Kissing number problem, it is considered. We can consider instead of the same size spheres, we can consider any size of spheres, and then we have this is a problem equivalent to the packing of spherical caps on a sphere. So the Tammes problem asks, suppose we have n congruent non-overlapping spherical caps, and on the surface of a unit sphere. So we have to find the packing with the maximum diameter of spherical caps. And this problem is also solved. It's solved now up to 14 and for 24. For n less or equal to 14 and for n equals 24. Here we have you can see people some solution that he thought first. He found bound. Infinity means he also shows that that approaches optimal density pi over square root of 12 into dimensions. Yeah, so the Waterwagen considered the case of 5, 7, 8, and 9. It's very interesting paper. Dancer, it is his habilitation. Habilitation thesis. He considered cases 10 and 11. Robinson 24, and recently we published a paper with Alexei Tarasov the case because of case 13 and 14. Okay, now return to packing. What happened in 1998? Thomas Hales, he actually used realized based on ideas Laszlo Feist-Todt that published in his book in 1953. He actually has a plan how to prove that. And he in 1998, Hales announced a proof of the Kepler conjecture. And the paper was published 8 years later, as I remember, right? Or 2006, probably, yes. 8 years later, because it was a computer-assisted proof, and people actually, it was impossible to check. It is understood because he considered, like, as I remember, it's about 5,000 cases. It is not like simple computations. And I remember that the first version of his program, it was just several months. Probably he needs computer time. But later, in the beginning of 2000, Hales organized some group of people who worked on computer verification of his proof. And 2014, Hales announced that the completion of formal proof using automatic proof checking. So now we can say that it is actually it is a proof. Yeah, because it is published at the same time in 2 journals. I mean, 2006 in Annals. It was shorter paper, and whole journal, Discrete Computation Geometry. This whole volume, it was about his proof, Hales Ferguson proof, and what was written that it is the first time probably it is in mathematics. Reviewers believe in 99%, 99% that is correct proof. It is interesting that because in mathematics we have 0 or 100, right? We cannot like 99 or so. Okay, anyway, now it is people agree. I cannot say that people satisfied by his proof, by Hales proof, but however we have no something better. Just only this proof. Okay, the next, I mean, if you consider sphere packings in 2016, Marina Lizovskaya actually announced her proof of her conjecture about that E8 is the optimal packing in 8 dimensions, and soon, just a few days later, Kohn, Kumar, Miller, and Radchenko joined to Marina and published the same result about Leach lattice in 24 dimensions. Actually, it was a very old conjecture known from at least from 19th century, and so it was big one. I am very like this her proof. I mean, it's a beautiful proof. I believe, she's. I was very upset when Marina got Fields medal because I believe she's. It is like very interesting, unexpected. Yeah, I knew Marina before. I met Marina before, and Bondarenko. I met them in Oberwolfach, but however, that's like could not even imagine that about that proof. I expected from other people, like there are several people who work in this direction, but we got this proof from Marina. Okay, let us consider now the rest of time. I will consider. I have 20 minutes, about 20 minutes. I will consider some what I discuss the result about 4-dimensional packing, because now the most interesting case is dimension 4. The same happened in the Kissing number when you 3 dimension 3, 8, and 24, and most interesting case was dimension 4. This still is open. I mean, like, because uniqueness still not proved. And for packing, I also think it is a very interesting dimension 24. What I'm going to discuss today. First of all, let us consider the 24 cell. 24 cell is one of 6 regular polytopes in dimension 4. In dimension 3 we have 5, right? Platonic solids. In dimension 6 we have 6. Or in dimension 4 we have 6. One of them is very interesting. It's called the 24 cell. it is easy to consider all vectors, total vectors. We have that they have two zeros component, two zero components, and two components equals one or negative one, plus minus one. Then this vectors formed vertices of a regular polytope that is called the 24th cell. He discovered in 1842 by Ludwig Schlafly. Okay, you can see here projection of that, right? Of the projection to the mesh side. I'm not sure that you can see something from that, but look at this beautiful sculpture by Adriano Agnano, and you can see here it is a Penn State sculpture. It is a stereographic projection of the 24th cell. You can see here open door, right? I gave a talk here. It was first time when I removed this this figure from my presentation, because it was of course not all people know this sculpture, this the 24th cell. Okay. I actually let me explain what in dimension 4 actually the conjecture is that the Kissinger number is 24, namely that are vertices of we have a unit sphere, and all of them with centers of the vertices of the 24th cell. It was conjecture also very old. I don't know, it is probably Corky, Zoltar, Focus knew that this conjecture, because they considered like 150 years, minimum 150 years it's known. It was as a conjecture. And I published paper, it was first announcement 2003, it was published short notices, but I used some some computation, and after that I just to publish full paper was published only 5 years later, because I tried to avoid any some computations, because I have to all computation has to be confirmed. Yeah, and let me give you a proof. The proof I just actually there is some. Let us consider the following polynomial. This is a precise coefficients. Like exactly as this, right? Let us consider the polynomial of degree 9, right? And now we can prove two lemmas, lemma A and B. First lemma says the following: suppose they have unit vectors, in other words, it's points on the unit sphere, in four dimensions. Then the following sum, we have m vectors, and that the following sum is greater or equal to m squared. Here we have this is a polynomial f sub 4. Of the inner product of these two vectors. It will be number, right? This sum is greater or equal to m squared. Actually, proof of this looks like complicated, but proof is actually it is only a few lines, because using some positive definite properties of so-called Geiger-Bauer polynomial, because if you consider this, this polynomial decomposition in Geiger-Bauer polynomials. Degree 4, this give you exactly all coefficients will be positive, non-negative. Sorry, because some of them are zeros also, like 6. I remember 6, 8. Other positive. So it is a few lines, but the second one in my paper say 20 pages. Out of 32, right? At least 30 pages to prove the following lemma B. The lemma B says the following: suppose we have the same sum, the same polynomial, everything the same, and the same m vectors. then the sum is, and with one more constraint, namely the inner product is for distinct vectors. I mean, when k is not equal to L, is less than 1/2. For points in a sphere, that means the distance between two points is at least angular distance at least 60 degrees. Then the sum is less than 25m. So we know that it's greater than m squared and less 25m. Then immediately imply these two lemmas imply proof of the Kiss number 24 by the following way. We consider Kissing arrangement. Kissing arrangement means, I repeat, Kissing arrangement. We call Kissing arrangement on the sphere if angular distance is at least 60 degrees. In other words, the inner product of these two vectors is less or equal to 1/2. So that from one side, if we have this, for two lemmas, we have this inequality. The sum is less 25m and greater or equal to m squared, and then we obtain immediately that m is less than 25. That means, that means you cannot be more than 24 vectors. This is a solution, but this is a solution, but nothing about uniqueness, because I will show later some. Okay. What we know about four-dimensional packing, the actual definition of what is a checkboard lattice d sub n. The n is nodes points in the integral points in dimensional space such that sum of coordinates x1 plus and so on xn is even. It's even number. Yeah, what we know about D4, that the dual is also D4. And by the way, the 24 cell is self-dual, because in the dual polytope for D4 for the 24 cell is also 24 cell. Exactly. That's what is also it's another equivalent. Sorry, equivalent formulation. The density is delta 4 is pi squared over 16. It's about that. The center density is we divide density by volume of the ball with this dimension. The center density in the 1/4, 0.125. And what is known, the first, I mean, there are some bounds. The first good bounds, Bancone Elkes 2000, I forgot, 2002 probably. It's also Ennals paper. Henry Kohn and Nom Elkes proved that the found is this bound, 0.13. It was a little bit, using KSDP, it was slightly improved by Delat, Oliveira, and Frank Valentin, and if you compare, you can see it's a little bit improved. So SDP gives some semi-definite programming, gives some improvement, but not much. Okay, so just still very far, right? If you it is also using like some linear programming, like in the case of Cornelkes, or semi-definite programming, like in the case Delat, Oliveira, and Valentin. But still actually not clear how to solve the problem. Let me present the 24 cell conjecture. The 24 cell conjecture, I call it actually to my terminology. Of course, it's a conjecture, all experts use this conjecture, but I gave the conjecture name. Yeah, and the people actually use this now. I'm proud that I gave this name. Conjecture is the following. Consider consider a Voronoi decomposition of any given packing P of unit spheres and in 4 dimensions. The minimum volume of any cell in the resulting Voronoi decomposition of P is at least as large as the volume of a regular 24 cell circumscribed to a unit sphere. What I mean? Actually, it is but not necessarily. Okay, what do we have? We have a unit sphere, right? And let us consider spheres around this unit sphere, and try to find just around. We don't care about like that is far from that, right? And we consider the Voronoi decomposition. Look at the cell Voronoi cell of the central sphere, right? And we have to prove that the volume that the maximum volume happened when this sphere around the central sphere are vertices of a regular 24 cell. Yeah. So this conjecture actually, if you compare with 3 dimensions, we have infinitely many different packing. It is not true, by the way. It will be different. I mean, not the densest packing. But in this case, in dimension 2, of course, is yes. Yes, we have a hexagon. It will be there also. This is a similar problem with a hexagon. And it is still open in dimensions, similar problem in dimension 8 and 24. I believe it we have also corresponding 8 and least lattice and like of regular. I believe it is it can be proved. I mean also local. So it is a local version of the density problem in dimension 4. Look like very simple. I mean, geometric problem, right? About 4 dimensions. Yeah, if you solve the problem, you will solve. You will immediately prove the problem. Okay, just I'm explain that this packing you can reduce for packing of spherical caps. It is more or less clear because some shadow. Yeah. There are different methods here. This analysis of methods, not so many area arguments like Weierstrass and Coxeter uses contact graphs that used by mostly in 3 dimensions. Schut and van der Waal, they consider it a dancer, and we also use this Leach, by the way, also distance graph. With Tarase, we also use this approach, contact graphs. But in the recent, only for we know only not recent. It's also not recent. It's almost how many years? 40-something years, right? Already they are programming almost 50 years. And SDP also SDP 12 years probably. And semi-definite probably 2 more methods. And I mean, if you look at the list of methods, not so many. Actually, just just a few methods we have to say packing. Okay, let us discuss what we have about this uniqueness conjecture. The uniqueness conjecture, I just to remind you that what the uniqueness conjecture is that in the Kissing arrangement in 4 dimensions is the 24 cell. I mean, we have 24, namely, if we already proved that Kissing number is 24. That means, you know, if we have 24 points in a sphere, unit sphere, then they have the distance at least 60 degrees. Then it is the 24 cell. This is conjecture. Here we can see some result. LP bound gives, we are looking for this number, I mean like upper bound, what gives some method. This number is 25. 25. It's about 25.6. Actually, it's found by Lattice and Sloan. They used polynomial 9. I remember that Aristide and Babenko from Ekaterinburg, they found actually optimal polynomial for linear programming of degree 23, but it's just slightly greater than, slightly less than, this 25. And my bound was, it was not optimal. My bound was, his number is 24, this 865. This, I try to find how far it is from 24, because if it equals 24, that means exactly we have uniqueness, but it's still far, right? Actually, it was not optimal, but I remember that the optimal was like 24.6, because I use this polynomial, like more simple polynomial than you can consider it in another one. The first publication using application of semi-definite programming by Bashok and Valentin in 2008, they used polynomial 3 variables of degree 7, and they have better bound. Look at their Mittelman and Valentin. They consider it high degree polynomial using semi-definite programming in 2010. And look, it's decrease. The bound decrease, right? Like 24.1, 24.09, and so on, it decreased. And I remember that it was 10 years ago, right? I remember when I met Frank Valentin, and he said, okay. It is, he believes that time that soon will be found exactly polynomial, say some degree, right? I don't know, 15, 16. And that gives you exactly, that gives solution of the uniqueness problem, but it not happened. And just recent publication, oh, sorry, it is published 2019, oh, sorry. Yeah, it is published already. I forgot change. Last year, Machado and Oliveira, they consider it high, actually not the same polynomials, they just reduce the only symmetric polynomials, and so this bound is not so, a little bit slightly different, but also based, of course, on the semi-definite programming. And they found for 15 still decrease, right? 24,062 and 16, 24,056 still decreasing, but now it is not clear. What is the degree of these polynomials? I mean, do we have something when we have exactly 24? Maybe it is a little bit strange. From one side, yes, it is decreasing. On the other side, it's not clear. Can be like exactly, do we have, they exist or not, polynomial that give us exactly 24. So it is open problem. It is extremely important problem, because it is actually it can be considered as a first step for solution of the problem of the optimal density in dimension 4. Yeah, because if you have no uniqueness, nothing to discuss. Actually, it is clear. Yes. Okay. Unfortunately, I have just almost okay. Let me just 3 minutes, try to finish to consider what we have. Just how can be developed method. Okay, let me show you the table. Okay, here we can see different bounds, different methods from linear programming and semi-definite programming. This bound is some polynomial of degree 1, right? And this is called Delsart bound, or linear programming bound. right? What I did, I just to put found some actually this function is a non-positive and in the interval -1, 1/2. But what I did, I just to give I considered some interval t this function can be positive, and I improve this a little bit and I proved that the Kiss number solve the Kiss number in dimension 4. This is Bashok-Valentin bound semi-definite program. And recently I found also extension of this Bashok-Valentin using it is combination of these two bounds. You can see here this one more bound. I hope that that can help to solve this the uniqueness problem. Yeah, here we have some extensions, and let me finish this. I'm sorry. Sasha, can I have 3 minutes to discuss the isoparametric problem?
Okay.
Okay. Yes. Okay. It is very interesting. Like there are 2 steps, I believe. One step it is try to prove uniqueness, and then as the next step to consider some geometric problem, because you can do nothing. We need some geometric problem. There is a very interesting area. Unfortunately, nothing happened during last 70 years in this area. Like last result probably it was 1948. It is isoparametric problem for polyhedra. The last result I know that phase thought result 1948. Can you imagine? Nothing. I mean, the problem is the same as for in 2 dimensions. We have a polyhedra, and to find we have isoparametric quotient. I mean, in this case, squared volume divided by cubed area of a surface area, right? This isoparametric quotient, and try to be as maximum as possible. I mean, like if you fix surface area to find the maximum volume. What is known as Lindelof and Minkowski proves the following theorem. Let us fix number of faces, and they prove it is 19th century theorem. They prove that considers the all convex polyhedra of the same number of faces. Then this polyhedra has the highest isoparametric quotient. Then it is circumscribed about a sphere which touches each face in its centroid. I mean, because here we have the one of the crucial things that is circumscribed, not any polytope. They have to be circumscribed. Yeah, the proof is not so complicated, but Lindelof first mentioned, and Minkowski found that proved also some existence. Lindelof missed this step about existence, but Minkowski actually completes his proof. Yeah, okay. What we need here, it is, I repeat, it is proved in 3 dimensions, and later, like say also 7 years. It is not complicated to prove this theorem for any dimensions. What we need is reduce immediately for uniqueness problem in 2 dimensions to prove the following conjecture. Conjecture is the following. Suppose we have not any polytope. We consider this we consider sphere packings, unit test. Suppose we have a unit packing, right? And actually, this we consider the centers of this packing as a polytope, as the vertices of a polytope, and the conjecture is that the volume of Voronoi cell, if we have some Voronoi cell of center point. Okay, we have a center sphere, right? At one point, vertex, and around that, you know, we have a spheres that formed also polytope vertices, vertical polytope. And we have a Voronoi, we can consider Voronoi cell, and then the volume of Voronoi cell achieves its minimum if P is circumscribed about the central sphere. It is that means, you know, the same sort of Lindelof-Minkowski theorem with one constraint, namely it is not any, we cannot do any moving because we have a constraint that is a unit sphere, they cannot overlap. Right. But it is of course a big difference. From one side, Lindelof-Minkowski theorem, it is a theorem about we try to reduce, try to move vertices, but in this case you cannot do everything. I mean, like it seems to me that a complicated problem, but in this problem plus uniqueness actually more or less directly, there is also a third one problem, another one problem. It is imply the solution of four-dimensional problem. Thank you.